Okay, so now we're going to talk about the rank of a matrix, R-A-N-K. The rank of the matrix is technically the number of linearly independent rows or columns of A. And the way we defined it is by this Greek symbol here, rho, over the matrix A, and the rank is, at the most basic level, the minimum of the two values of rows and columns. So if you have whichever of these two values is the smallest is the rank of the matrix if every value in there is linearly independent. So that's the basic starting point for finding what the rank is. So if we have a matrix A here equal to, say, 1, 0, 0, 1, you can see that except for multiplying all these the values in this column by 0 or the values in this column by 0, these are not factors of each other in any way. So both of these columns and rows are linearly independent. And we can talk about that in another video, or you can find it somewhere else. But so the rank of A as it sits up there as 0, 1, 0, 0, 1 is less than or equal to the minimum of 2 by 2, because it's a 2 by 2 matrix. So 2 by 2 is the smallest one. So the rank is going to be less than or equal to 2, because that's the smallest value. But since both of these are linearly independent, it's going to be equal to 2, because there's no value smaller than this. Linearly independent columns or rows decrease this value a little bit. So this is actually also called full rank, because you use one of these values as rows or columns to determine if it was a rank. So if you just use this equation and you get the value that you need, it's considered full rank. So an example of not being full rank is if A were equal to 1, 3, 7, 2, negative 6, negative 14. Now, the basic rank equation here, or inequality, I should say, is the minimum of 3 by 2, because it's a 3 by 2 matrix. Okay, so the rank is going to be less than or equal to 2. But as you can see up here, these two columns are not linearly independent. This is actually 14. I apologize. If you multiply this column by negative 2, it's going to equal this column. So these two are not linearly independent. There's actually only one linearly independent column or row in this case. So that's going to equal 1, which is the number. So rank has to equal 1. That was kind of confusing, and I'm going to restate that one more time. So the normal rank based on the rows and columns is 2. But since there's only one linearly independent column or row, because multiplying this by negative 2 would equal this column, there's only one rank. The rank can only equal 1 because of one linearly independent column. So the rank can either be less than or equal to the smallest number of rows and columns, or equal to the smallest number of linearly independent rows or columns. So the full rank of this is actually 1. And there you go.